Well, good afternoon, everyone, and welcome. Welcome to Illinois Institute of Technology. Welcome to this annual really outstanding lecture series we have in honor of Darsh Wassan. Everyone here who's a friend of Darsh Wassan and who helped make this lecture possible every year, I'd like to thank you for your gifts towards this and to really say that this has turned into something really wonderful. This is the 10th Wassan lecture. And each one has been better than the previous one, and I'm sure the same thing will be true today. As you know, Darsh has had every position in this university, apart from president. I guess you never wanted to do that, Darsh. And has really had a long career here at the university, and obviously he's a member of the National Academy of Engineering. He's a very famous chemical engineer. But the great thing is he's spent his whole career here. Actually, as a young professor, he and his wife actually had children here on campus, lived in the housing on campus for a number of years. And really, it's a wonderful thing to be able to honor Darsh and bring just outstanding lecturers here to give the Wassan lecture. And as I said, this year is no different than any of the previous years. We have another outstanding person who's come to talk to us about a very timely subject, and that's climate change. And, you know, Professor John Holdren, who's currently professor, the Heinz Professor at the university, at Harvard University, started his career at MIT, where he was actually an engineer working in aerospace issues, and actually started to like physics more, and ended up going to Stanford to do his PhD. And from there, he ended up as a faculty member at UC Berkeley, and then a faculty member at Harvard. And while he was at Harvard as a faculty member, he really was called to the White House to go and join President Barack Obama when he came in as president, to be really the chief technology officer for the White House and the person responsible for really making sure that issues of policy related to science and technology were forefront in any discussion, and making sure that science and technology was something that was considered whenever major decisions had to be made. You know, he's also in the National Academy of Sciences and the National Academy of Engineering. He has won many awards and many accolades, and all of them well-deserved. And today I'm really looking forward to his talk on global climate change and U.S. interests. John, can I ask you to make your presentation?
Well, thank you very much for that kind introduction, and it certainly is a great honor to be here to give the Wassan lecture this year. I'm going to try to cover a lot of ground, and I start with a capsule description of the essence of the energy climate challenge. It starts with the proposition that without energy there is no economy. Energy is essential for meeting basic human needs, for driving industry, creating jobs, economic growth. But secondly, without climate, there is no environment. Climate is the envelope within which all other environmental conditions and processes have to function. And if you distort that envelope too much, you can interfere with the operation of all of those other environmental conditions and processes, many of which we depend on for our well-being as acutely as we depend on economic conditions and processes. Without economy and environment, of course, there's no material well-being, there's no civil society, and there is no security, either personal or national. And the essence of the challenge is that for a very long time, the world has been getting most of the energy that its economies need in ways that are seriously disrupting the climate that its environment needs. In the rest of this talk, I'll elaborate in various ways on that proposition in these steps. You can read faster than I can talk, so I'll let you look at this outline, but it is something of a drink from a fire hydrant. Some of these slides may go by a little quickly in terms of the amount of content on them compared to your capacity to digest it all. I will be posting these slides on the website of the Belfer Center for Science and International Affairs at Harvard's Kennedy School of Government, so that they will be findable on the web if you want to take a closer look at any of them. Starting with the origins of human-caused climate change, if you look at the 150 years between 1850 and 2000, the growth of the population of the world and prosperity over that period brought an astounding 20-fold increase in civilization's total energy use. And most of that growth came from the fossil fuels. From 1850 to 1950, it came mostly from coal. From 1950 to 2000, growing twice as fast as in the previous century, the growth came mostly from oil and natural gas. You look at the picture in 2015, the data are not quite available for everything for 2016 yet, but what one sees is that even today the world remains overwhelmingly dependent on fossil fuels. 82% for the world as a whole, even higher dependence for China and the United States. The countries listed here are the 5 biggest emitters of carbon dioxide from fossil fuel combustion in the world. You see that China has surpassed the United States, both in economy in purchasing power parity corrected terms. In market exchange rate terms, not quite yet. In purchasing power parity already, China is the biggest economy in the world. They passed us in carbon emissions in 2007 and are now much bigger than the United States. But the real message here is all of us, all around the world, still depend very heavily on fossil fuels. And if you recognize that basically coal is CH, carbon and hydrogen, oil is CH2, natural gas is CH4 mostly, wood is CH2O in simplified terms. All of that carbon becomes carbon dioxide when these fuels are combusted, and with today's technologies, all of the carbon dioxide goes straight into the atmosphere. The other combustion product is water. It goes into the atmosphere too, but the water additions have only a tiny effect on the natural water cycle, while the carbon dioxide additions have a big effect on the natural carbon cycle, and very importantly for our purposes, on the concentration of this important heat-trapping gas in the atmosphere. What you see here is the history of the emissions of carbon dioxide from 1850 up until roughly the present, the emissions from human activities. The dominant emissions at the beginning of that period were from forestry and other land use change. The dominant emissions for most of the period thereafter came from combustion of fossil fuels. The record of carbon dioxide content over the millennia, which we know from looking at the content of air bubbles trapped in layers of ice in the Antarctic and Greenland ice sheets, that record of CO2 concentration shows the gradual rise. This is 10,000 years roughly of atmospheric CO2 in the big graph here. You see a gradual rise in the CO2 content from the agricultural revolution, and when the industrial revolution comes along, you see this spike, this extraordinary rise in atmospheric carbon dioxide concentration that is blown up in the period from 1750 up to the present in the little inset. Well, it's not quite the present. Today, the atmospheric concentration exceeds 400 parts per million. In this graph, which came from the Intergovernmental Panel on Climate Change report in 2007, it hadn't yet reached 400. But as noted in red there, in 2016, the concentration was 45% higher than its value in 1750, which is generally taken to be the beginning of the Industrial Revolution. We've added some other heat-trapping gases as well, methane, CH4, nitrous oxide, N2O, from energy systems and agriculture largely, as well as chlorinated, fluorinated, chlorofluorocarbons, hydrofluorocarbons from consumer products and industry. They are plotted up here in terms of what in the trade is called radiative forcing. That literally means how hard you're pushing on the climate with the changes in the Earth's energy balance that you're creating with these additional heat-trapping gases in the atmosphere. The result, not shockingly, in fact, it was predicted many, many decades ago, first predicted, in fact, in 1896 by Arrhenius, the forcing the pushing on the climate from these heat-trapping gases has been warming the Earth. This shows the temperature of the Earth related to a baseline, which is the 20th century average. And what you see, the shaded rectangles represent the decadal averages, the averages for each decade. 2016, of course, the hottest year in this whole long period, which is called the instrumental record, the period over which thermometer measurements were dense enough to meaningfully define a global average surface temperature. 2015, the second hottest year. 2014, the third hottest year. Of course, there is bumpiness in the trajectory. There's variability of both the natural influences on climate and some of the human influences, and that produces the bumpiness. But what you basically see is that from the middle of the last century onward, the warming effect has dominated the bumpiness that comes from this other variability. And in fact, humans reversed, through the influence of these greenhouse gases, we reversed about 6,500 years of natural cooling. This is a reconstruction of the last 12,000 years of global average surface temperature with the instrumental record at the very end. And what you see is that we were in a very long-term natural cooling trend heading perhaps over the next 10,000 years into another ice age. We fixed that, but we overcompensated. The natural influences doing this were largely perturbations, variations in the Earth's orbit, in the tilt of the Earth's axis, in the precession of the axis, like a top precesses. Those effects, amplified by feedbacks in the climate system, brought us the ice ages and the interglacials between the ice ages. They're still operating, but they are now a minor factor on the short run being hundreds or thousands of years compared to the human influence. Global warming, though, is something of a misnomer. The term global warming implies something that's uniform across the planet, that's mainly about temperature, that's happening slowly and might even be good for us. After all, what can be the matter with planting a little earlier in the spring, swimming a little later in the fall? Maybe not such a bad thing. The reality is different. What's actually happening, as we'll see, is highly non-uniform. It's not just about temperature. It's rapid, not slow, compared both to historical rates of temperature change and compared to the capacities of both ecosystems and human systems to adjust. And it's harmful for most places and most times. Some places for some period of time may get some benefit from the warming, but as the warming grows, the pervasiveness of its negative effects will overwhelm any temporary and local positive effects. A more descriptive term, therefore, is global climate disruption. I started proposing in the 90s that that's what we should be using instead of global warming. My attempt failed utterly, and everybody still talks about global warming. Global disruption does not flow so readily off the tongue, and a lot of us these days are just settling for climate change, as in the title of these remarks. But to emphasize, climate change is not just about temperature. Climate is the pattern of weather. The averages, the extremes, the timing, the spatial variables, the spatial distribution of all of the weather variables, hot and cold, cloudy and clear, humid and dry, what's coming down in drizzles, downpours, and hail, snowfall, snowpack, snowmelt, how hard the wind is blowing from breezes to typhoons. All of that is climate, and climate change entails disruption of those patterns. Again, not just the averages, but the extremes, the timing, the distribution. Global average temperature is just an index of the state of the very complex climate system as expressed in those patterns, and small changes in that index correspond to big changes in the system. It's really very much like the human body temperature. When your body temperature goes up 2 degrees Celsius or 3.6 degrees Fahrenheit, it's telling you that there's something amiss in the underlying system, the complex system that is your body. Even though that temperature change doesn't sound by itself like very much, it's exactly the same with the climate. The changes are, moreover, very non-uniform. This is a picture of the average change in temperature compared to a baseline of 1951 to 1980. For the whole year 2016, January to December, the average for the whole globe in that year was 1 degree Celsius above the 1951 to 80 baseline. But look what's happening in the far north and in some of the northern mid-continent regions. 2 to 4. 2 to 4 compared to 1. Climate is changing 2 to 4 times faster in the far north than on the global average. The changes that are occurring include a warming ocean. Sea level surface temperatures are going up, as we'll see, quite significantly. Arctic sea ice is shrinking, as you see very dramatically in this diagram, 79 to 2016. 79 because that's the first year in which we had satellite observations that enabled us really to see the extent of the Arctic sea ice. This, of course, is floating ice, and when it disappears, it doesn't affect sea level, but it drastically changes the energy balance of the Arctic. The sea ice reflects most of the sunlight that hits it. The bare ocean absorbs most of the sunlight that hits it. And so the disappearance of the sea ice is accelerating climate change in the far north and is one of the reasons it's faster than climate change in most other places on the planet. The changes include disappearing glaciers. This is a quite dramatic picture taken from exactly the same place in August 41 and then August 2004 of one of the many coastal glaciers rapidly receding. Mountain glaciers are doing the same thing. We are seeing accelerating losses of ice from the Greenland ice sheet. As you see in this diagram, the post-2010 decline is faster than the pre-2010 decline. One of the things we have learned in the last decade is, in many respects, climate change and its impacts are actually accelerating. They're not proceeding in a uniform way. They're going faster and faster. We now know that the Antarctic continent is also losing land ice. We didn't know that until relatively recently when we had satellites making gravimetric measurements that could actually measure the mass of the ice underneath the satellite. And now we know that Antarctica is adding to the ocean as well. Not surprisingly, then, sea level rise is itself accelerating. The 2010 to 2016 trend, 6 millimeters a year, is twice the trend from 1992 to 2016, and that was twice the 20th century average. So sea level rise is now going up at about 4 times the rate it did over the 20th century. Well, I should have said that loss of those ice sheets is one contribution to that. The thermal expansion of seawater is another. As it gets warmer, it expands. That raises sea level. And indeed, I see a typo there. I put pumping twice, but pumping of groundwater faster than groundwater is being replenished also adds to sea level rise. So we're doing a number of different things that are causing this. We'll see what harm it's doing later. But in addition, human additions of carbon dioxide are acidifying the ocean. About a third of the carbon dioxide that we've added to the atmosphere has been taken up by the ocean, roughly the top 80 meters initially, and then it mixes around. That carbon dioxide, in a very simple reaction, H2O plus CO2 produces weak carbonic acid, H2CO3, and that is reducing the pH of the ocean, increasing its acidity. We'll see later what that's doing. So what are the U.S. interests at stake in global climate change? Why worry about climate change? What harm is this really doing? Well, we need to understand, first of all, that climate governs, and therefore altering climate will affect the availability of water, the productivity of farms, forests, and fisheries, the prevalence of oppressive heat and humidity, the formation and dispersion of air pollutants, the geography of disease, the damages we have to expect from storms, floods, droughts, and wildfires, the property losses from sea level rise, the expenditures we have to make on engineered environments, how many dams and dikes, how much of the world do we have to air condition to protect ourselves, and the distribution and abundance of species, those we need, those we love, and those we hate, all being changed in their distribution and abundance. How global change and responses to it are affecting specifically the interests of the United States. Start with environment, damage to life, health, property, and ecosystem services, from increased frequency and or intensity, sometimes both, sometimes one or the other, of heat waves, wildfires, powerful storms, torrential downpours, floods, sea level rise, ocean acidification. National security, the potential for conflict drawing in the United States, resulting from climate-driven political instability. in and refugee flows from other countries. Syria, the situation there, the political situation, having been aggravated initially by an incredibly severe and long-lasting drought, a good example. Additional demands on U.S. military forces for rescue and recovery after climate-linked weather disasters. And impacts of climate change on bases and capabilities. The biggest naval base in the world is the U.S. Naval Base in Norfolk, Virginia. It's about 3 feet above sea level. It's already suffering flooding on high tides from rising sea level. Military capabilities, ability to carry out military operations in conditions of extreme heat, for example, or under other forms of extreme weather. Seriously compromised. The Department of Defense, interestingly enough, is probably the most forward-leaning federal government department when it comes to recognizing the threat of climate change and proposing to do something about it. Interestingly, Secretary of Defense James Mattis urged President Trump to stay in the Paris Climate Accords because of the military's recognition of the magnitude of this problem. The economy. Impacts of climate change on economic infrastructure, wealth, income, and livelihoods. The economic benefits of the United States leading in technological innovation to reduce emissions in ways that create jobs, save energy and therefore money, and create economically valuable side benefits like reducing smog. When it's hotter, smog is worse. When it's less hot, smog is not as bad. And smog converts into medical cost damage, again, to the economy as well as to health. And finally, the economic risk of conceding leadership in climate mitigation and adaptation technologies to other countries, forcing the United States, if indeed we do cede leadership, it will force us to import these technologies rather than making them and exporting them, a damage to our economy. So let me talk a bit about the harm that is already occurring from climate change. There was a long argument for some years about when we could be sure that the goal of the UN Framework Convention on Climate Change to avoid dangerous human interference in the climate system would have been made moot, when we would have come to the point where we were experiencing dangerous interference. It is clear now that that point was passed some time ago, that we have been experiencing for probably 15 or 20 years dangerous interference in the climate system. Around the world, we are seeing in various combinations increases in floods, drought, wildfires, heat waves, pest outbreaks, coral bleaching, permafrost thawing and subsidence, coastal erosion and inundation, and the power of the strongest storms, all plausibly linked to climate change by theory, by models, and by observed fingerprints, meaning the pattern in which these changes are occurring. Heavier downpours leading to flooding. This is a rather elementary proposition. A warmer atmosphere can hold more water, and if it's holding more water, more can come down at one time, and does. The rate at which extreme one-day precipitation events have occurred in the contiguous United States been going up dramatically. We are seeing 1,000-year floods occur much more frequently than that. These are pictures from East Baton Rouge, Louisiana in August 2016, where they got 20 inches of rain in 3 days. We saw something worse in Houston this year, where we saw 3 500-year floods in 3 years. Makes you wonder about that term, 500-year flood. Some folks think it's paradoxical that you could have more floods and more droughts from the same cause, but it is in fact well understood. Higher temperatures mean bigger losses to evaporation. The soil gets drier. More of the rain that falls, falling in extreme events, means more is lost to storm runoff rather than percolating into the soil. The mountains, of course, get more rain and less snow. That yields more runoff in the winter, and that leaves less for the summer and fall when droughts occur. Earlier spring snowmelt does the same, and you also have some changes in circulation patterns that have contributed to droughts in many parts of the world, the Amazon particularly. Wildfires, much in the news lately. The number of areas burned annually in the United States and over much of the rest of the world has been going up drastically. It's a bumpy curve. There's a lot of interannual variability, but the trend is unmistakable. just to leave it here for a moment, if you look at the wildfires that have been occurring in Northern California, the fingerprint of climate change on those wildfires is absolutely clear. In 2015, we burned an unprecedented fraction of Alaska. One of the extraordinary things about wildfires is in the far north, in Alaska, across Siberia, across northern Canada, it used to be only the forested areas that burn. Now the tundra is burning in the far north. The tundra is burning. Never happened before, not in the time of human occupation and reporting. Heat waves. This is a very complicated diagram. I apologize for that, but it is telling us a very important thing. This shows the probability distribution for the summer temperature anomaly on land in the northern hemisphere. The middle of these distributions is the mean. Out on the ends, you find the extreme events. What you see is that in the 1950s, 60s, and 70s, the distributions were very similar. They very closely resembled the classic normal distribution, which meant if you go out 3 standard deviations, you're looking at a 1 in 700 year hot event on the high end. Then you look at what happened in the 80s, the 90s, and the 2000s as that distribution moved to the right. A modest temperature change in terms of the mean, how warm the average summer was, led to an extraordinary increase in the frequency of extremely hot summers. What used to be 3 standard deviations in terms of how hot the summer was. What this means, in short, is stated at the bottom. The amount of land in the northern hemisphere that experiences a 3 sigma hot summer in any given year has gone up by 50 to 100-fold since the 50s, 60s, and 70s. Absolutely extraordinary. And this is having profound effects, including on the ability to work outside. The capacity of people to work in agriculture and construction in the hottest months of the year has already gone to 0 for some parts of the world. You cannot work outside doing any heavy work of any sort without dying of heat stroke. And that is spreading, and we will see that shortly. But just a schematic illustration of the same thing, those observed changes. Observed changes, that's not theory what we just saw, that's observation. Big increases in extremes go along with small shifts in average temperature. That was expected. It was predicted. This diagram just shows how it works. You move the mean a little bit, you move the extreme a lot. Pest outbreaks. Great example, unfortunately, is provided by the pine bark beetle, which gets 4 breeding rounds into a single warm season, a single summer, instead of the previous 3. The combination of more pine bark beetle breeding with trees weakened by heat and drought has produced millions of acres of dead trees, which, by the way, then become tinder for the wildfires. And the wildfires, by the way, the biggest cause of wildfires is what? It's lightning strokes. And lightning is increasing under climate change. One of my own postdocs was the first to document that particular phenomenon, made the cover of Science. So we are aggravating the wildfire problem in multiple ways at one time. Coral bleaching. Coral bleaching experience this year was the worst seen anywhere over time that we've been watching, over the period that people have been diving and recording what's happening on coral reefs. The new film, Chasing Coral, which is available on Netflix, is an astonishing documentary showing the death of corals all over the world from a combination of warming and acidification. Really stunning problem. Permafrost. Permafrost is thawing all across the far north. When permafrost thaws, the structures that are built above it collapse. You see an example from Russia on the left, an example from Fairbanks, Alaska on the right. Rising sea levels are producing increases in coastal erosion. In the Arctic, this is aggravated by the fact that the sea ice has disappeared, and so the coastal structures are exposed directly to storm waves that previously couldn't make it ashore because of the ice. Coastal inundation, another very dramatic picture. These are for East Coast cities in the United States, coastal cities, showing how many days a year the streets were flooded at high tide. And you see the 50s are the little short blue bars at the top. The 2010 to 2015 period are the long blue bars at the bottom. The steady increase in flooding days coming from sea level rise, already a big problem in coastal cities. And stronger storms, when you look at the pattern of the strongest tropical cyclones, the strongest cyclones in every basin have occurred since 2012. You could add one here, October 2017, Ophelia, the only time a Category 3 hurricane has ever made it into the eastern Atlantic. Mind-boggling. Never happened before. So let's talk about projections. It's harder to talk about the future than to talk about what's already been observed. This is one of the things scientists mean when they talk about uncertainties in climate change. But these I call plausible projections, things that are likely to be true under the emissions assumed going forward. I like this quote variously attributed to Yogi Berra and Niels Bohr. Prediction is difficult, especially about the future. But if we try it, looking ahead at temperature and its impacts, they're going to grow for decades ahead under all emission scenarios. This shows the historical record up until now on the left, and to the right in color, the record of projected temperature change from low emission scenarios where the world takes drastic action to reduce emissions of the heat-trapping gases. Those are the blue lines. The red lines are continuation of more or less business as usual. That doesn't mean no action. It just means only slow improvements in energy efficiency and in reducing the amount of CO2 released from the energy supply system. It's quite sobering to recognize that at any given time, we are not seeing the full impact of what we have already added to the atmosphere. That's because it takes a long time for the oceans to catch up with changes we've caused in the heat balance of the atmosphere. The oceans are a huge balance wheel in the climate system. It takes the ice even longer to catch up with what has been done in terms of influencing the atmosphere and the oceans. And so it takes hundreds to thousands of years for the ice that's going to melt to finish that process of melting and the motion of the glaciers into the sea. Last time the temperature was 2 degrees Celsius above the 1900 level. We're now 1 degree Celsius above it. The last time we were 2 degrees Celsius above it, sea level ended up 4 to 6 meters higher than today. 4 to 6 meters. A meter, for those of you who forgot your high school chemistry or physics, is 3.3 feet. Last time temperature was 3 degrees Celsius above 1900, 3 degrees rather than 2, a place it looks like we're likely to head unless we take very aggressive action. Sea level, that was 30 million years ago. There were alligators in Greenland. There were palm trees in Alaska. Sea level was 20 to 30 meters higher than today. But there's a huge difference, and we've already seen that in that first diagram between the blue curve and the red curve. There's a huge difference in the amount of harm to be expected depending on what we do. The picture on the left is the temperature change expected under that aggressive action scenario. The picture on the right is the temperature expected under business as usual. The global average temperature increase under business as usual, 5 degrees Celsius or more, 9 degrees Fahrenheit average, and 2 to 4 times that in the far north and some of the mid-continent areas. The biggest uncertainty about the future, and I emphasize this because some folks are saying, well, the future is uncertain, so let's not do anything. We don't know enough to take action. The biggest uncertainty about the future is whether we take action or not. It's not the scientific uncertainty, it's not the modeling uncertainty. The biggest uncertainty is what society decides to do. So when you hear somebody arguing it's uncertain, let's not do anything, recognize that they're putting their thumb on the scale for inaction, which means more harm, bigger damage. In the high emissions case, if we do not take drastic action, we expect by the second half of this century that heat waves of the sort that killed 70,000 people in southern Europe in 2003 would be the summer norm, the average summer year. By 2070, that would be an unusually cold summer in southern France and Spain and Italy. In much of the world, by the second half of this century, under business as usual, working or exercising outside in the hottest part of the year would risk death. Regions prone to drought and wildfires would experience multiples of today's worst. By multiples, I mean 3 to 5 to 6 times the number of drought days, 3 to 5 times the annual average area burned by wildfires. By the middle of the century, under business as usual, the world's coral reefs and the biodiversity they support would mostly be gone. And by the way, the coral reefs are the second biggest reservoir of biodiversity on the planet. The biggest is the tropical forests, also affected particularly by climate change. Two biggest reservoirs of biodiversity being affected adversely by climate change. Sea level rise under the high scenario could reach 2 meters by 2100. And would likely reach 10 meters or more by the time it came to equilibrium. 33 feet. Think about 33 feet of sea level rise for coastal areas in this country and others. Tom Towles, who does cartoons for the Washington Post, is my favorite climate change cartoonist. Does a lot of cartoons about climate change. I like this one a lot. I'll just give you a second to look at it. Let's talk a little more about the possibilities, things for which we've identified a mechanism but can't yet put a number on how likely it is. What you don't know can hurt you. Uncertainty doesn't mean everything will turn out to be better. It could mean things will turn out to be a lot worse. The most worrisome possibilities, often called tipping points, greatly accelerated sea level rise happens much faster because of rapid disintegration of the Greenland and Antarctic ice sheets, rapid release of methane and carbon dioxide from thawing permafrost and warming Arctic sediments, which would accelerate climate change overall and all of its impacts, a massive drying and fires in the formerly moist tropics with enormous damage to local peoples and to biodiversity, a crash in ocean fisheries resulting from warming, acidification, oxygen depletion, toxics, overfishing, all simultaneously stressing our ocean resources. These are possibilities. We know they're possible. We don't know how likely they are or when they might occur. And finally, collapse of the Atlantic meridional overturning circulation, which is what drives the Gulf Stream, a determinant of local climates. You could have very paradoxically, really, much colder winters in Northern Europe while the world as a whole is warming. Another one of those possibilities, the accelerating sea level rise. There have been recent studies that are quite disturbing in this respect, with respect to Greenland. Greenland, more and more of the surface ice in Greenland is melting in summer, providing a warming surface rather than a reflective surface. Algae and detritus are landing and growing there, making Greenland darker, meaning its ice is shrinking even faster. We saw evidence of that acceleration in an earlier graph. In Antarctica, disintegration of the fringing sea ice shelves could greatly accelerate the flow of land ice to the sea. A chunk of the Larsen sea ice shelf, bigger than the state of Rhode Island, in fact, I think it was about as big as Maryland, broke off earlier this fall. The question of CO2 and methane from Arctic soils. Arctic permafrosts contains 2.5 times as much carbon as the atmosphere contains today. There's 2.5 times as much carbon stored in that soil, which is now thawing and exposing that carbon to decomposition and being released to the atmosphere. It's 3 times as much carbon as is in all the living vegetation on the planet. That is a tipping point in waiting that nobody really knows what it will do. This is a stunning picture. This is a methane burst crater. What you have is that methane becoming gaseous, having been produced by decomposition of this thawing permafrost, produces a gigantic bubble, and eventually that bubble underground bursts and produces a crater like this. These craters are popping up all over Siberia. We have direct measurements to show that methane emissions from the far north are increasing. Methane is a much more potent greenhouse gas than carbon dioxide per molecule. So the stuff that comes out as methane is doing much more damage than the stuff that comes out as CO2. Although neither one is wonderful, methane is even worse. It is, as I said at the bottom of that slide, busting out all over in the Arctic. So what can we do? What are society's options for affecting these different kinds of outcomes? I like this quote from Lao Tzu: if you don't change direction, you'll end up where you're heading. As we've seen, where you're heading is not very nice. So what can we do? There are only three options faced with the climate change challenge. The first one is mitigation, steps we take to reduce the pace and the magnitude of the changes in global climate that we're causing. The second is adaptation, steps that we take to reduce the damage to our well-being that is done by changes in climate that nonetheless do occur, that we're not able to avoid through mitigation. And the third is suffering the adverse impacts and the social disruption that are not avoided by either mitigation or adaptation. Concerning those three, we're doing some of each. As you've seen, we're doing some suffering. We're also doing some mitigation. We're also doing some adaptation. What's up for grabs, what's up for debate is the future mix of those three. How much mitigation are we going to do? How much adaptation? And how much suffering is that going to leave? Minimizing the amount of suffering can only be achieved by doing both a lot of mitigation and a lot of adaptation. Mitigation alone won't work because climate change is already happening. We've seen that. It cannot be stopped in its tracks, both because of the momentum in the climate system and because of the inertia in the global energy system. The global energy system, again, more than 80% fossil fuel, represents a global investment of $25 or $30 trillion. That's how much it would cost to rebuild the global energy system today, all the power plants, the transmission lines, the oil refineries, the pipelines, the drilling rigs. $25 or $30 trillion ordinarily turns over in a time of 30 or 40 years. If you have a $30 trillion investment that turns over in the normal course of things in 30 or 40 years, you cannot turn it over overnight, no matter how badly you may want to. Adaptation alone won't work because adaptation gets more difficult, costlier, and less effective the larger are the changes in climate to which you're trying to adapt. Think about a low-lying Pacific island, 1.5 meters on average above sea level. For such an island, for a population that lives on it, adaptation equals evacuation. That's not much in the way of adaptation. So what we need is enough mitigation to avoid unmanageable climate change and enough adaptation to manage unavoidable climate change. Lots of possibilities for adaptation. I list some of them here: heat, drought, and salt-resistant crop varieties, including using genetic engineering to produce them, strengthening our defenses against tropical diseases, preserving and enhancing green infrastructure, that means ecosystem features that protect against extremes, preparing hospitals and transportation systems for heat waves, power outages, and high water. Rather elementary form of adaptation is moving your hospital's emergency generator from the basement to the roof, which after Sandy we learned to do. Building dikes and storm surge barriers, avoiding further development on floodplains and near sea level. And what I like to point out, including to members of the U.S. Congress, is that these are things we should be doing even if you don't believe climate is changing. There have always been storms, always been droughts, always been wildfires, always been heat waves, and we've always been underprepared. We should be investing in better preparedness for those kinds of events, even if we didn't know that climate change is increasing their frequency or their severity. Mitigation possibilities. Certainly reduce the emissions of greenhouse gases and soot, which also absorbs incoming sunlight and warms the earth. Particularly, of course, from the energy sector, but reduce deforestation, which also contributes these gases and soot. Increase reforestation, afforestation. Reforestation means putting trees back where they used to be. Afforestation means growing trees where there weren't any before. Trees are nature's solution for pulling carbon dioxide out of the atmosphere and storing it. We should be doing more of that. Unfortunately, it looks like if we do that to the max, we will do about a quarter of what we need to do to get on a trajectory that corresponds to those low emission futures that I showed you. We could modify agricultural practices to reduce emissions of greenhouse gases and build up soil carbon. Conceivably, we might get desperate enough to scrub greenhouse gases from the atmosphere technologically. That'd be very expensive. Greenhouse gases in the atmosphere, carbon dioxide today is 400 parts per million, 0.04%. A lot more expensive and difficult to do that than to remove it from the exhaust gas of a power plant where it's 20% of the gas you're dealing with. Geoengineering, very controversial topic. The idea is to create cooling effects offsetting greenhouse heating. How could we create cooling effects? Well, a simple and non-controversial way is to paint roofs and highways white rather than letting them be gray or black so that they reflect solar energy rather than absorbing it. That will help with the urban heating effect, but only 2 or 3% of the planet 2 or 3% of the land area of the planet is covered with highways and roofs, and so you're not going to have a big effect on the global problem. The more controversial approaches include things like trying to put mirrors in space to deflect some of the sunlight away from the Earth, or inject reflecting particles into the stratosphere, as volcanoes do, periodically cooling the Earth for a few years when there's a big volcanic explosion. The problem is that injecting sulfate particles into the atmosphere, which is what most people have looked at, into the stratosphere, will also deplete the ozone layer. So you have a little problem of out of the frying pan and into the fire. Chemists are looking at the possibilities for injecting stuff into the atmosphere that would not interfere with the ozone layer. We'd have to be pretty desperate to do that, but you can imagine, given the trajectory of impacts that we are seeing, countries becoming desperate enough to seize on some of these kinds of possibilities for slowing down the effects of greenhouse gas additions. How much mitigation do we actually need? How soon do we need it? Well, limiting the global average surface temperature to 2 degrees C or less, which is the goal embraced officially by the European Union in 2002, by the G20 in 2009, embraced at the Paris conference, and Paris added an even more ambitious goal, try to keep it below 1.5 degrees centigrade as an aspirational goal. It's not that that's safe. We're already experiencing impact at 1 degree C, as you've seen. So there's no real red line at 2. There's no argument that says, well, as long as we're below 2, we're safe, and above 2, we're cooked. The fact is we're just sort of increasingly cooked as we move from 1 to 2 to 3 to 4. But to have a 50% chance of meeting that officially agreed goal of staying below 2 degrees C, you'd have to stabilize the atmospheric concentration of the heat-trapping substances altogether at the equivalent of 450 parts per million of CO2. The CO2 alone is now at 400. To get there, to achieve this, developed country emissions, industrial country emissions like our own, need to have peaked around 2015, and they have to be going down rapidly after that. Developing country emissions have to peak no later than 2025 and decline rapidly after that. So let's look at what Obama did in the light of these realities. Another of my favorite quotes, the first law of holes: when you're in one, stop digging. First term, $80 billion for clean and efficient energy in the Recovery Act, early 2009, recovering from economic recession, about an almost $900 billion effort. Nearly 10% of it was for clean and efficient energy, the biggest boost for clean and efficient energy anywhere in the history of the world. Hundreds of millions of dollars for the Advanced Research Projects Agency on Energy, looking for outside-the-box solutions. 6 new energy innovation hubs, partnerships between business, national laboratories, and universities to advance clean energy technologies. The first ever fuel economy carbon dioxide combined tailpipe standards for light-duty vehicles, for cars. and fuel economy standards for trucks for the first time. Something like 30 building and appliance energy efficiency standards. An interagency task force for the first time looking at adaptation, lifting up adaptation as co-equal in importance with mitigation, led by the Office of Science and Technology Policy, my office, the Council on Environmental Quality, and the National Oceanic and Atmospheric Administration. A reinvigoration of the U.S. Global Change Research Program, 13 agencies, $2.7 billion a year, trying to understand better the processes of global environmental change, particularly climate change, and what to do about it. The launch of a new national climate assessment of climate change impacts on the United States. The first time that the government had calculated and used in its decision-making a social cost of carbon, an estimate of how much damage we're doing for every ton of carbon dioxide we put into the environment. And the first national ocean policy, the first time the United States has had a national ocean policy and a national ocean council to implement it. The second term, of course, saw President Obama's climate action plan announced on a sweltering hot June day at Georgetown University outdoors. Perfect venue for announcing a climate action plan. President constantly wiping perspiration off his brow. I was very fortunate. I was just off to the left in this picture, but I was sitting in the shade. First ingredient, cutting carbon pollution in America, mitigation. Second, preparing the United States for the impacts of climate change, adaptation. And third, leading international efforts to address climate change. The U.S. emission target, which President Obama announced in Beijing in November 2014 for 2025, President Obama, President Xi stood up together and said the United States and China recognize this as a huge challenge for the 21st century. We are the two biggest economies, the two biggest emitters. We're going to lead together in addressing this challenge. And by the way, I think the Paris Accords would never have succeeded except that a year earlier Obama and Xi stood up together and said the biggest developing country and the biggest industrial country were going to lead and cooperate on this issue. We were on track to meet the target that Obama announced. The record under Obama, comparing 2008 and 2016, fossil energy use went down, renewable energy use went up 42%. Electricity from wind went up more than fourfold. Electricity from the sun went up more than 40-fold. Carbon emissions from energy went down more than 10%. The Paris Agreement, a really big deal. 195 nations embraced intended nationally determined contributions for emissions reductions to 2025 or 2030. There were accounting and reporting provisions that were made legally binding. Achieving the voluntary target was not legally binding. That's how we avoided it being a treaty that the Senate would have to ratify. If we had to submit it to the Senate, we know what would have happened. It would have gone down the drain. All countries to revisit their commitments at 5-year intervals with a view toward increasing ambition. The bargain included the industrial nations providing assistance for mitigation and adaptation to developing countries, reaching $100 billion a year by 2020 and remaining at that level for at least 5 years. And under a side agreement called Mission Innovation, 20 of the industrial nations, led by President Obama, agreed to double their government clean energy research and development over a period of 5 years. When you look at the CO2 emissions, industrial CO2 emissions means not industrial country emissions. It means emissions from fossil fuels, cement manufacturing, gas flaring. The world's CO2 emissions look like they might have peaked in 2014, but we don't know yet whether that was a real peak or a fluctuation. We have to hope it was a peak. We have to hope that the world's emissions will continue to decline. It looks like they also did decline in 2016, but the full data are not in yet. Looking ahead, what is Trump doing and what should we do? And I quote here Trump's director of the White House Office of Management and Budget, who said, "We're not spending money on climate change anymore. We consider that to be a waste of your, that is, the taxpayers' money." So what Trump is doing and proposing so far, he's appointed climate contrarians to key posts. to the head of the EPA, to the Office of Management and Budget, to the Department of Interior. He's proposed drastic cuts in budget and authority for the EPA. He is cutting or proposing to cut climate change monitoring and analysis. They're saying that uncertainty is too great to act, but they don't want to reduce even the scientific uncertainty by investing in observation and research. Big cuts proposed in energy research and development at the Department of Energy, zeroing out, this is proposed, Congress hasn't accepted it yet, zeroing out the Advanced Research Projects Agency for Energy, cutting other energy R&D by $2 billion, rolling back or re-examining all of President Obama's executive orders on climate change, the Clean Power Plan, the methane strategy, the inclusion of climate change in environmental impact assessments under the National Environmental Protection Act, doing away with the social cost of carbon as an ingredient of government decision making. All that's been done by executive order, cutting back U.S. support for adaptation and resilience both at home and abroad, even though it makes sense even if climate isn't changing. And by the way, the elimination of the Clean Power Plan is not actually having any effect on coal production. The Clean Power Plan wasn't even in operation at the time President Obama announced its abolition, except for one part. The one part that was in operation was the Retraining Coal Miners for Better Jobs program, which Trump has succeeded in eradicating, a triumph. Agency science and technology budgets. This shows what President Trump has proposed for fiscal year 18 versus fiscal year 16, which was continued for fiscal year 17 in the omnibus bill. The percentage change in nominal dollars, the only thing that goes up is defense, and that's at the far left. The non-defense caps have to go down in proportion, and the percentage decreases in all these other science budgets are the red bars going down. The one blue bar going up is the nuclear weapon part of the Department of Energy. So the defense stuff goes up, everything in non-defense goes down. What should the science and technology community do? One, don't be discouraged. Keep doing your work. We should all keep doing our important work while looking for alternatives in the cases where federal funding does decline. Look to states, look to firms, look to philanthropies, figure out how we can get this important work funded going forward. Keep talking about the results and their implications. Do not be intimidated by what seems to be a political climate of opposition to facts. Facts remain important, and the science and technology community continues to need to speak truth to power. We need to get better at explaining the science to lay people, not just what we know and why it matters, but how we know it, the diversity and robustness of reinforcing lines of evidence, the sources of credibility in science. People need to understand that one single contrary publication or blog post is not going to overturn 200 years of climate science. The imprudence of ignoring the science, the two-sidedness of uncertainties, that uncertainty means not just that it might be better, but that it might be worse than your current best estimate. And the rarity of scientific revolutions overturning the scientific consensus. There are a lot of folks who are holding their breath waiting for a scientific revolution to overturn the laws of thermodynamics so that we can have a miraculous energy solution that is pollution-free and that solves everything. They're going to turn blue long before the laws of thermodynamics are overturned. And I think everybody in the science and technology community should be tithing 10% of our time to public and policymaker education and to policy and political activism, providing citizens and legislators with the knowledge they need to defend respect for science in policymaking. Trend is not destiny. Thank you very much. So the question of whether electric cars really reduce pollution is one that is re-examined constantly. In fact, I have my classes in energy do these calculations. And the conclusion we invariably come up with is that electric cars do reduce energy use and pollution, but not probably by as much as their advocates generally argue. First of all, in today's world, we still generate 2/3 of our electricity by burning coal. Electric cars would reduce pollution a lot more if the electricity were all generated with cleaner sources, with nuclear, with renewables, for example. Secondly, the production of the batteries actually takes a lot of energy. You more than make that back over the life of the car, again, if the energy is cleanly and efficiently generated. So yes, they're a benefit, but probably not as big as usually advertised, but there'll be a bigger benefit as we transform gradually our energy economy in the direction of greater efficiency in generation and greater cleanness in generation.
You're saying that the current structure of, in the current energy infrastructure, the car probably is not as useful as it could be.
It's not as useful as it could be, but it is useful. We benefit from electric cars, and of course we also benefit on the highway where the electric car is not in fact generating any pollution. I had a friend, the late Lee Shipper, great colleague and energy expert, who said there's no such thing as a zero emission vehicle, there is only such a thing as an elsewhere emission vehicle. And that's the story with electric cars. But again, if we make the elsewhere cleaner also, we will increase the benefit.
However, when you ask a question, I'm going to ask you to use the microphone so the rest of the audience can hear the question.
John, in the 1960s, there was a major political tipping point when the attitude toward environment changed from the early part of that decade, when talking about the environment was for the nerds, and at the end of that decade we passed the Environmental Protection Act and the Clean Air Act. But what caused that tipping point, and what could we learn from that to make something like that happen now?
A lot of what caused the tipping point was extremely dirty air in many of America's cities and extreme water pollution, including rivers burning because they were so polluted, air so polluted in the Los Angeles basin, and I lived there in the early 1970s. You couldn't go out to the track and run because the air was so polluted. You started choking if you tried to run. You felt the tightness in your chest. People all over America were experiencing that dirty air and dirty water. That's what they understood environment to mean. And so we passed, as you say, the Clean Air Act, the Clean Water Act, established in the early 70s, the Council on Environmental Quality, the EPA, the National Environmental Protection Act. If you ask what's going to do that today, what I think is doing it is the increasing conspicuousness of impacts of climate change in people's everyday lives. More and more people are experiencing the torrential downpours, the like of which they never experienced before, the floods, the like of which they never experienced before, the droughts, the heat waves, the frequency of the most powerful storms. And again, in the interest of time, I didn't show you some of the worst stuff I've got. But one slide I didn't show you and I wish I had is the latest results from Princeton's hurricane model, which shows that under a mid-range emission scenario, the number of Cat 3, 4, and 5 hurricanes making landfall on the east coast of the United States will double over this century. Now again, no model is perfect. Maybe they got it right, maybe they got it wrong, but it is highly suggestive. And we know why hurricanes are getting stronger under climate change. The ocean water from which they draw their strength is getting warmer. And the warm layer from which they draw their strength is getting deeper, and this is a more subtle point. That means that the storm waves that are generated by the hurricane can't churn up as much cold water because they can't reach it. And that churning up of cold water by the waves has been a self-limiting factor on the power of hurricanes. That's all changing. So as that stuff changes and as people make the connection, and we could use some more help from television meteorologists in making those connections. But as people make those connections, they see it happening around them, they see it happening on their TV. We already have about 70% of the American public who believe that climate change is real, humans have something to do with it, we should be taking action against it, but they rank it very low on their list of priorities. In 2010, they ranked at number 18. If you ask them what keeps you awake at night, what are you worried about? They're worried about their jobs, the economy, their kids' college education, their health, their retirement, whether we're going to go to war. Climate change in 2010 was number 18. It's now up to about number 7. If we can get it to number 1, 2, or 3, people will start voting on the basis of whether the candidates are taking a sensible position on climate change. I think we'll get there.
Hi. Hi, great talk. I watched a documentary recently called Merchants of Doubt that discusses how big oil companies are funding kind of climate change denialism and skepticism in the US. So for example, ExxonMobil is funding like climate change denial think tanks at the same time that they're rebuilding their oil rigs to be higher to accommodate for rising sea levels. And so I was wondering if you have thoughts on what like everyday citizens can do to try to like combat.
Yeah, I do have some thoughts. First of all, the oil companies are a mixed bag. They have invested for a long time in organizations that are propagating denial and muddying the water, but they're investing less over time, investing much less now than they used to. Most of the big oil companies are using an internal cost of carbon of about $70 a ton of CO2 in their internal decision making because they are resigned to the fact that society is by and by and within their decision time frame going to be embracing a substantial carbon tax. They are diversifying their business plans, figuring out how to make money in the transition from oil and gas to cleaner sources. They are investing and looking at things not only like biofuels and solar photovoltaics, but looking at carbon capture and sequestration, which would enable them certainly to burn natural gas for longer. And I think, by the way, that mastering and making affordable carbon capture and sequestration technology is going to be crucial to an emissions path that we can live with. I have had occasion over my career to discuss and meet privately with the heads of most of the major oil companies. To a person, they actually understand that climate change is real and humans are causing it. And their issue is how fast do we have to change our business plans to accommodate that. I'll say one more thing. The influence of big money in American politics is pernicious. There are a couple of great books out about that. One that I particularly like is one of our senators from Rhode Island, Sheldon Whitehouse, has written a book called Captured, which traces the influence of money in American politics all the way back to the founders and how they thought about it and how they never anticipated the kind of thing that we're now experiencing in big money that is also anonymous money in American politics. And Senator Whitehouse has some ideas about what to do about it. I recommend that book to everybody who's interested in American politics and why we are not doing better.
Well, Professor Holdren, thank you very much for a very interesting talk. We will now have a reception outside here in the Herman Union Building, and it'll give you an opportunity to talk to Professor Holdren directly, and invite you all to join us at the reception. Thank you very much.